We have a resistor, a capacitor connected like this. These are the polarities, we must be careful. And we have a common current here. There are two currents flowing inside the inputs. This must be 0. There are two voltages here and here in the inverting and the non-inverting inputs. These voltages must be equal because we have a negative feedback configuration for our ideal op-amp. This means that the voltage here at point X, this is point X, must be also 0. This concept is known as a virtual ground. Doesn't mean that it's actually grounded, no current leaks to the ground per se. However, it's important to understand that this node always has a voltage of 0. This allows us to do great things. Now, taking the Ohm's law for the resistance here, the voltage across it must be Vin minus Vx over R1. Vx obviously is 0. Now there are many ways to proceed from here, but this is the one I prefer. I will use a similar law for the capacitor, for the impedance of the capacitor. The voltage across the capacitor must be equal to Vx minus Vout. Again, these are the polarities. Vx must be equal to 0, and the impedance of the capacitor is 1 over C1s. This is the Laplace form, obviously, of the impedance. You can write it as j omega or any other way. Now, because the current is common, I can say that this is the same as this. V in over R1 must be equal to V out over 1 over C1s, which gives us this result. If you are familiar with Laplace transformations, this is nothing but an integral. If we perform the inverse Laplace here, we get that V out is 1 over C1s with a minus in front times the integral of V in respect to dt plus an initial voltage that we might have had here on V out, because we must be careful when we work with capacitors and we do inverse Laplace transformations, we get integrants and things like that. And that's it. That's basically the op-amp integrator. We can plot V out in respect to V in, and we have the operation that we wanted, okay? We have a step function here, and this output integrates the inputs. It has a constant here in front, but there is a problem here, and a very serious one at that. Problem is that if you notice, the more we have a voltage like this, a DC voltage, the more the output is getting higher and higher and higher and higher. The DC voltage at the input is causing the output to grow indefinitely. This will cause much problems that we are not going to go into much detail now, but this is something that we need to fix. If we plot the out over V in, we notice, in respect to the frequency, we notice it's this function here, right? The more we go higher and higher on the frequency scale, the output over the input must be lower and lower and lower and lower. But in lower frequencies, as you see, it gets higher and higher and higher and higher. And if we had a DC input, this will grow up indefinitely. This is obviously a low-pass amplifier or a low-pass filter. Why? Because it allows the very tiny frequencies to pass, but as they go higher, V out over V in gets very, very small. Now, we still have this issue here, and we're going to fix it with a very simple way. I'm going to add the resistor here in parallel to this capacitor. The voltages stay the same here. And well, I can say that the R1 can be written as an impedance Z1. And this part of the feedback loop can be written as a total of Z2. I can write my previous equation as this. And this is the more general equation for the inverting op-amp configuration. Now I can write Z2 as ZR2 in parallel to ZC1. Z1 is ZR1. And if I do the algebra, I get this result. And this result says to us that when we have small frequencies here, this fraction gets very, very small. It gets very close to 0. So we have 1 over R1 plus 0, 1 over R1 times minus R2 over R1. So V out over V in will be equal to a constant value. And when the frequencies get higher and higher, this becomes a typical integrator as we have seen previously. This is known as a leaky integrator. And if we plot V out over V in, they'll have this behavior. From the beginning up to a specific point, the output over the input again must be equal to R2 over R1, because we have the absolute value is plus R2 over R1. When we get to one point, the point being 1 over R2C1, or 10 times lower than this, alright, we get this behavior, the integrating behavior, as we again saw earlier. This point is called the cutoff frequency, and behind it is the bandwidth of our configuration. Why is it called a bandwidth? Because we have what is known as a low-pass filter for this range of frequencies. Our integrating ability, as we notice, shifts to slightly higher frequencies. Because in smaller frequencies here, we will not see integrating behavior. What we're going to see is a typical low-pass amplifier with a typical inverting op-amp configuration. Now, this works again as a low-pass filter. It does not integrate DC voltage. Alright. And therefore, we are protected from the DC voltage. We have fixed our configuration. Now let's look at this exercise. We have an op-amp that works as an integrator, again, the improved op-amp, which has R1 this, R2 this, and the capacitance of the capacitor this. Alright, first and foremost, we are asked to find the cutoff frequency. Again, I will have my equation here of the output of the input. And the cutoff frequency must be 1 over R2C1. Alright, this is the speed. So the speed is equal to 2 pi fc, which fc is equal to this. This is about 160 hertz. Right, what is the bandwidth of our configuration? The bandwidth must be equal to minus 162 or plus 160 hertz. And what is the integration range? We saw that we start integrating from the cutoff frequency and onwards, but up until which point? Because we have an amplifier, a low-pass amplifier that works as an integrator too, there is a point that V out over V in that's going to be equal to 1. If you remember from earlier, the output has a constant value and then it gets lower and lower and lower up until it goes to 1. From there onwards, the output over the input will be lower than 1, smaller. So the output will no longer be amplified from that point onwards. So that's why I will say that this is the final point at the frequency domain that we have an integration. The frequency now must be much, much higher than the cutoff frequency. Therefore, let me write it like this. The frequency here will be much higher than this part. So S will overwhelm 1 over R2C1. Now R2 will be simplified with this R2 and the configuration is the same as we had. I will call this frequency as SL. Again, FL must be equal to 1 over this. This is 160 kilohertz, about this. Now, the integration range must be what? From the cutoff frequency to this frequency. So it's FS to FL, 160 to 160,000 hertz. Also, it includes the negative frequencies as well. Now, the next part of the exercise asks us, what is the output if the input is this? All right, we have our equation here. This is a very more simplified form. R2 has been simplified here and here. And we notice that the frequency now is what? Much higher than 1 over R2C1, much higher than 160 hertz. Therefore, I am in the integration range. Therefore, this term overwhelms this term, and I have that V out over V in, is equal to this. Again, this is the same as the integrator that we had without the extra resistance. Performing the inverse Laplace operation, I have that V out is equal to this. Obviously, I don't have any initial voltages here, otherwise I would be very careful. Now, what I'm going to do is a simple algebra operation, and this will be my result. Be careful because the integral of the sign is minus cosine, so minus with minus becomes plus. Now we draw the inputs in respect to time. This is the periods, and the output will be equal to a cosine that starts from this point 8 and goes like this. It has the same frequency, but instead of a sine, it's a cosine. All right, let's go to the second part. Second part asks us to do the same for a sine. Second part asks us to do the same for a signal that has this frequency. Again, I'll write my equation here. I notice that my frequency is much lower than the cutoff frequency. All right, more than 10 times lower. Therefore, I can safely say that this term overwhelms this term, and C1 and C1 get simplified. Therefore, V out over V in must equal to minus R2 over R1. Notice again that in smaller frequencies, the output over the input is a typical inverting op-amp configuration. The output now must be equal to R2 over R1 is about 10 to the power of 3, times the same input signal. Now if I remove this, I can write the input here, period of 10. I put squiggly lines here because this and this are very, very far apart. If you see it in your books written like this, don't be confused. And I plot the output as a signal, a sign with a negative sign in front and the size of this. And that was it. If you find these videos valuable, subscribe to the channel right now and don't miss another electronics video. Study well and take care.